So let me start. So our last session in the workshop is actually the panel. So for the panel, we're going to invite back the keynote speaker, Victor, and we had a chance to actually you had a chance to hopefully listen to his talk and his messages. I just quickly want to introduce the other panelists. Tansh Bennett. Tansh is actually a hardware engineer veteran, and he's incredibly knowledgeable about all things hardware. He's the one that was the main author of this work last year, the workshop on Panopticon, which is this maintaining counters in DRAM, which is an idea that is starting to have legs in industry. We also have Daniel Groos. Daniel is widely known for his work on showing attacks on hardware, not just Rowhammer, and I believe actually also side channel attacks on DRAM. He did some work on that, but also CP, like he's sort of the famously known for the Meltdown and Spectre attacks that we've all been let me rephrase this. The industry has been fixing for the past many years now, and will continue to fix in the future. And finally, Moin, who is not yet online. Moin said he's in a taxi cab going to the hotel at Iska, and he's going to join us probably in the next 5 or 10 minutes. So we're going to save him for last in terms of presentation. The format of the panel is every speaker, every panelist has a budget of 3 to 5 minutes to make a point of view. They can choose to make a point of view. They can use slides. They don't have to use slides. They don't want to say anything, that's fine. It's completely up to them to how they want to spend this time. And after that, we're going to have a roundtable discussion. And again, we encourage the audience to ask questions as much as possible. So we're going to start with Tansh, if that's okay. Tansh, do you want to share your slide, or you right me to actually share it?
I'm set up to share it.
Okay. Hold on one second. Great. We can see your slide.
Can you? Is it full screen or is it showing the menu bar?
It's showing. It's not full screen. No.
Okay, let's see if this changes it. Okay.
Yeah. No, it's full screen.
Right. So thank you for the introduction. Like most of the people here, I share the overall concerns with disturbance effects in DRAM, and I believe that on current technology, they are set to increase. It's kind of an unavoidable side effect of crowding the cells closer together, at least the control lines closer together. The cells themselves are fairly well isolated and will be for a while, but the leakage occurs when the neighboring control lines weaken the gate transistor on the neighboring cell. So I think that's going to continue, and people will be inventive in finding ways to get at it. Maybe the DRAM industry will come up with a solution in terms of defensive algorithms. I'm concerned with what happens if they don't. One of the topics I see mentioned occasionally and often with some confusion is the effect of ECC and encryption. And people vary from saying, oh, if there's ECC, nobody can change the value, so we're safe. There's not a lot of discussion of encryption. A lot of DRAM is encrypted these days. So I just thought I'd spend a few minutes bringing people up to speed on what the consequences are in these various scenarios. So the left-hand column here, no ECC, that's currently consumer devices, PCs, phones, laptops, tablets. Despite all that we're saying here, DRAM is miraculously good. You can have a device which at least apparently has no errors in the DRAM for its entire working life. Even if it does have errors, they might be in parts you're not currently using or in values that don't show up doing anything particular, like a blip on a pixel on the screen. So a lot of devices simply have no error checking. that means that if people have a method of doing the row hammer or equivalent, they have unlimited control of the values, because if they can change bits, nothing's going to oppose them. The middle column represents where those are going. For various reasons, the DRAM vendors are putting single bit ECC on the die. The main reason for that is because the cells are expected to have increasing rates of soft failure due to refresh not working on the occasional cell. They can correct one bit. They have no mechanism to tell the host that they either corrected a bit or that there was an error they failed to correct. And in fact, they're not even very good at detecting 2 or more errors. There's about a 50% chance they don't even notice it. And if they do notice it, there's a good chance they make a correction, which is not the right one. So it really only works with 1 bit. With 2 bits, you're basically back in the left-hand column. And so most hacks do depend on changing more than 2 bits in a cell. So they'll go through. Occasionally, they'll get an extra bit inserted by the ECC getting confused. So they won't successfully create just the value they want, but often they will. So the on-die ECC is not going to make a big difference to row hammer because row hammer changes more than 2 bits. It works with patterns that changes that ECC can't fix. Even when you get up to server class symbol ECC, the story is better in that server class ECC can detect that the error has not been corrected. It's about 99.99% better, reliable at doing that. Maybe better. It varies slightly from vendor to vendor. But
is there a way for me to get the receipt?
Pardon?
That was, I think that was just an accident.
Yeah, I think he was accidentally online. So we can at least detect that the error occurs. We can't stop people changing the values. So that brings it to a variation of denial of services. Then the other row there is what happens if the data is encrypted, and it can be encrypted in all 3 scenarios. You know, I assume that even some cell phones and tablets encrypt the DRAM. There are various attacks that mandate that for servers. Most industry servers will nowadays encrypt all their DRAM. The main effect the encryption has is that an attacker really can't generate a desired value because they have no idea what the underlying value is. When they change bits, it's going to have been scrambled by the encryption. When they put it in, any bits they change will just create a different encrypted value, which is unpredictable. So in all 3 classes of device, you have a great similarity here. The attacker will no longer have control of getting a particular effect. They probably can't get control of the device, for example. They probably can't, you know, mess with the return stack or stuff like that because they can't create a desired value. But in all cases, they can create corruption. And in the first 2 cases that the consumer device is either present or future, they're probably not going to be detected because the ECC, the on-die ECC, which consumer devices will probably depend upon for years to come, doesn't have any reporting mechanism that can tell the application that there was something wrong. So only on servers do you ever have a detection and the ability to do something about it. Finally, okay. What's the worst case? What's the worst case for this? If we look at what's the cost to the user or the cost to the organization owning the server or owning the machine. In the first 2 cases, corrupted consumer devices, maybe they gain control of your device. They can certainly cause your device to seem unreliable, might cause you to try to take it in for replacement. Maybe the device, if there was a widespread attack, they could degrade the reputation of a device where that was happening. Pretty much similar in servers. The apps are detecting it, a smart OS could probably even recognize the signature of this kind of error and realize that it's occurring because of disturbance attacks rather than hardware. They are fairly distinctive in that all bits fail, and probably in a random way, in a non-repeatable way, I mean. So they are distinctive. The apps and the servers could do something about it if they're written to do that. But there's still going to be problems of, imagine you visited a web page and the web page downloaded an attack and your machine just regularly failed. You would feel probably from the user thinks the hardware is failing. That's what it looks like. So there's unreliability, there's reputation loss for that hardware. Maybe even it goes into a repair cycle and can't be fixed, that kind of thing. So there's still damage that can be caused by these attacks by malware in any of these cases. So ECC and encryption do vary the consequences, but they don't make it inconsequential.
Thank you, Tansh. We will take questions at the end after everybody had a chance to actually speak. So I'm going to ask Daniel to now present or choose to use his time budget whichever way he likes.
Hi. Yeah, I didn't prepare any slides here, but I basically wanted to pick up where Victor also topics that Victor also touched in his keynote. I'm less optimistic on that we will solve Rowhammer, and the problem is that it's an optimization problem. And we've seen that also in the table that we've just seen. It is an optimization problem, and engineers will always try to tweak the last bit of efficiency and last bit of performance out of that chip. And as long as that is possible, as long as we can do that, as long as we can optimize further and only gain efficiency and performance at the cost of increasing the risk, people will do that. And they will optimize it so that the risk is like, yeah, still tolerable, but the chip is as fast as possible, as efficient as possible. And that makes sense, right? We need efficiency, we need performance. But risk, who cares about risk, right? So that's why I think Rowhammer is here to stay and not going away. We're going to find very nice solutions that reduce the problem, and then engineers will continue optimizing, and it will be as big as before. Thanks.
Thank you. Very clear message and well delivered. Looking forward to the discussion, actually. Now I'm going to ask whether Moin is available. I'm not sure if you, Moin, had a chance to actually. I see your, yeah.
Sorry.
Okay,
give me 2 minutes. Please carry on.
Okay, so we will, yeah. We'll then open for discussion. You had Victor's the chance to listen to Victor, yeah. So okay. Are there any questions online? So I agree with Daniel very much. And in fact, one of the so speaking of people, so picking on Tansh's point, which is that people actually sometimes there's a little bit of inconsistency. Some people think that having a hardware solution that is state of the art is going to really eradicate or stop this problem. And I always remind myself, and I tend to follow that fallacy, remind myself that's true only if it's configured right. You might have a hardware thing that can do anything it wants, but like Daniel said, there will be a lot of push to actually configure that to really not take additional bandwidth from the DRAM bus if it doesn't have to. And maybe we can do this and the other thing in terms of optimization. And the solution is there, but it's not running the way it's supposed to run. So I'm also kind of think that Rowhammer is here to stay for a while, given sort of what I'm seeing.
So maybe to add to this discussion. So I just presented this very complicated attack, and where we need to synchronize with so many refreshes in succession in order to even see a bit flip. Should we not agree that if we get all the DRAM and all the systems to that state, that it would probably already be good enough? Or do we really need a complete Rowhammer solution that we know is always going to limit every single bit flip? Or is it fine to maybe live with a bit flip every now and then? And I'm looking at Stefan, by the way, because
I'm not on the panel. I'll let others actually answer.
Oh, you should be on the panel.
I don't think that people have reacted well to devices that are not reliable, and I don't see any reason why they should have to. I think that suggesting that we'll just get used to it and accept devices failing or being attacked.
No, so my point is that it is not going to fail. So these attacks, they are so complicated. There will never be a benign application that will ever trigger a pattern that will trigger a bit flip on this device. And even for an attacker, there will never be an attacker that will pull off an attack. I hope, but I have a very hard time in believing that anyone would ever launch an attack like this, because there are just easier options, right? To do. Yeah.
So let me ask you this. Go ahead, Daniel.
The problem that I see is that in other areas of security, we are making more progress. We are making other attacks harder. So it's only a matter of time until Rowhammer will be the cheapest option. Maybe it won't come, hopefully, right? But I wouldn't exclude that possibility.
That's also the case for Rowhammer, right? So the attacks today are already much harder than they were 5 years ago. And I expect that the attacks in 5 years will be much harder than today. So we are keeping.
I'm not sure. So for half double, for instance, we looked a bit at half double, and this is pretty much as simple as back in 2015.
What is hard to do when you have a threshold of 10,000 is not so hard at 1,000, and is perhaps the low-hanging fruit at 100. And we see in the technology that trend could happen. I'm sure the DRAM vendors are all diligently working to prevent it, but they have the competitive and technology reasons why, you know, the decline has happened and will continue to happen. It's only a matter of time. Either we find a completely different mechanism for DRAM, which doesn't have this, or we continue to live with this proven and juggernaut of DRAM and see these parameters decline. Unless there's a fundamental improvement in the algorithms, and some of the algorithms that work fine at 10,000 don't work at 1,000 or 100. So, because you're entering the realm where you're almost defending from regular programs, never mind from attacks. So, I don't think that saying, well, it hasn't happened yet, is a good defense against 5 years from now. I see it easier in 5 years, not harder. Unless the DRAM vendors really get serious about adding resources to the DRAMs and the channels to bolster the defenses, but their responses so far have been really just dabbling at the edges. I like what the way Daniel thinks, you know, that imperative to improve and take risks. It's very strong.
So, and let me portray sort of what the way I think about it is, so first of all, I have no idea what DRAM vendors actually do inside of their circuits, right? So maybe there is a possibility that there is some sort of combination. I mean, you know, Victor, you mentioned that you have to synchronize with refreshes, and that a lot of refreshing is very hard, and I'm sure it is. I don't dispute that one moment. But maybe there is something we don't know yet, because it's obscure. We don't know what's happening there. Maybe there is a different way of actually attacking that none of us have come up with yet. Well, I can see a scenario, hopefully it will never happen, where a nation state will buy some VMs on major cloud vendors in Europe and the United States and elsewhere. And one day they will just take down, you know, let's say 23% of all servers in the world. How? Not by actually exploiting a bit to infiltrate, but by doing what Tanj was saying, with which all these servers have strong ECCs, and they all, when you have a storm of errors, they all react in ways that, guess what? Nobody really understands today. They think they do, but how will a farm of servers react when you have massive errors in DRAM? We don't know. Nobody has run that experiment. And that would be serious. There will be lives lost because of that. And we've seen that the world is crazy, right? There are all sorts of crazies out there in the world with a lot of resources. I hope it's pretty clear to everyone by now. So that's sort of, I think, what motivates me at least to say that, yeah, I'm not so sure that this is not going to be.
It's interesting that denial of service on the network is a very big deal. And it's a blunt instrument. All it does is deny service. It doesn't get control. It doesn't do all those other things. But the fact that it became possible made it an industry, a clandestine industry, but it's definitely, you know, setting records every month. There's a new big DOS attack. If people realize that there are ways to create DOS attacks with disturbance effects, that will become a thing too. Hey, Moinidin, you're online.
Yeah, first of all, my apologies. I was supposed to arrive about 2.5 hours ago, but my flight got delayed and here I am. So hello, everybody. I think most of the points that are being made, like I was in a similar boat. And my take was, actually, if Kaveh, if you have the slide, I can just present it like in a minute.
So Stefan, can you share Moin's slides maybe?
Just one slide, yeah. And then, so my take on this is not just coming from security perspective, but also from reliability perspective, right? Yeah, just next one. Sorry, I had animations. Yeah, so we should not only just look for what we have right now, but 5 to 10 years down the line, right? And dealing with Rowhammer at about 100 or 200 from a hardware perspective is fundamentally different problem, right? Than dealing with 1,000 or few thousand. Your trackers become gigantic, right? Till now, we're thinking about trackers that take few tens of kilobytes at the memory controller or inside a DRAM chip. If you need 2 megabytes of tracker per chip, it's just a no, it just won't happen, right? People are not going to be buying those. Second, if your threshold is a couple of hundred, currently, if you take spec and you just run it, you will have several workloads that already have a few hundred activations within 64 milliseconds. So this doesn't just, this is not just an attacker versus defender. How do you just process normal workloads, right? It's not that you can just isolate different applications and think that everything is okay. Your application can itself cause bit flips in your own application, right? And fundamentally, I think we're a little bit narrow-sighted that we're thinking about Rowhammer. Rowhammer wasn't such a big deal 10 years ago. If we're thinking 10 years from now, why will Rowhammer be the only thing that we're concerned about? Devices become smaller, there are different leakage factors. We'll have even more failure modes, right? So just thinking about solutions that are just focused on Rowhammer, I think is a little bit narrow-sighted, right? We need to build better trackers. We need to build better mitigation techniques. SSDs are dealing with a lot of these issues. They give a little bit of space to protect the remaining space. DRAM doesn't really do that, right? A more proactive management of DRAM, where you use some amount of DRAM space to protect the remaining DRAM, might actually be quite useful. And a big hammer is ECC. Currently, we have ECC designs, but they're really focused on correction. They're not really focused on detection. Correction is the first criteria. What we really need to do is implement integrity protection at zero cost, right? So how do we get integrity protection and change those codes such that you actually get larger and larger protection for random bit flips? Reliability currently is either single bit flip happens or certain large granularity fails, right? People who design reliability codes think very differently. They don't think about intermittent failures. They think about permanent failures. How do we design ECC code such that we get strong detection, we get larger number of single bit errors that may happen because of row hammer, and we want larger granularity protection also. So this is actually a fascinating problem where we don't know the threshold, we don't know the failure mode, we don't know the kind of attack patterns that will happen, and we have to design something for the next 10 years. So largely in agreement with people, but my take is don't just think about, I know we are DRAMSec'. This is not just a security problem. At few hundred, you will have workloads that will have that many activations, right? So solutions that think that when this happens, it's like an anomalous behavior are really not going to be acceptable.
Yeah,
Go ahead, Daniel.
I completely agree with you. The notion that you presented here is more of a, although you say like it's not just a security problem, the approach, the notion that you took here is a security notion or approach, because you say we need to protect from something that we don't know yet. Whether it's whether we call it a disturbance or reliability error or whatever we call it, it will be some problem that will occur, and we need to protect from it. And that's a pretty generic security.
Yes and no,
notion.
right, Daniel? I have the entire machine to myself. I'm running only one process. There is no other process. There's no attacker. If I still get bad result, it's a reliability problem, not a security problem. My contention is, even if there is no bad actor, I can just damage myself, right? I won't call myself an attacker at that point, right? So there's a subtle difference, right? In security, there are two players. Reliability, a single player can just take an axe and put it on their foot.
That's right, but also in security, in many situations, you don't have multiple users on the same device. You have for instance, if you think about smart cards and all the research on fault attacks on smart cards, that's a single user device, but still you care a lot about what an attacker could do. And these are external effects, external attackers that are not on your device, but they control the environment. And here, if you say, yeah, there could be something that goes wrong and it's not necessarily a security issue, I don't think it's possible to separate reliability issues from security issues.
So I'm not saying that reliability is a problem, security is not a problem, right? I'm making the converse. Yes, security is the problem, but that's not the only problem. Reliability is also, in addition, a problem, right? And this notion that currently we have large caches, so application hammering may not happen. That misses one fundamental point, right? We cache at a line granularity. The row is 8 kilobytes. It has 128 lines. Even if you had a gigantic cache, you could actually just do 128 activations, regardless of your cache size, right? Now, if I go through the cache 2 times, I can do 256 activations. So it's really not, and 64 milliseconds is actually not, it's a gigantic amount of time. It takes typically about 1 to 2 milliseconds to fill the cache, right? So fine, you have 10x longer cache, larger cache, it might take 10 milliseconds. I can go through the cache 6 times. 128 times 6 is several hundred, right? That's why I'm fundamentally making this difference, that tolerating row hammer at several thousand is very different than tolerating row hammer at few hundred, right? So row buffer only helps if you're going sequentially, right? If I do A1, B1, C1, D1, and then after 100, I go through A1, B1, C1, A2, D2, that doesn't really help, right? So like hoping and praying will not work. Like the mindset for a few hundred is really, really a different mindset than a few thousand. Few thousand, you can really live in this world that there are attackers and then there are protectors and there are anomalous behaviors, and the application characteristics comes to help you, right? At few hundred, that safeguard just goes away.
We looked at performance counters some time ago already, like several years ago. And there it was surprising that just casually scrolling through some websites on Firefox would cause more cache hits and misses than, for instance, a flush and reload program that we were trying that was running flush and reload nonstop. Because flush and reload is not the fastest approach to get accesses to DRAM, because they are not interleaved, because you always flush and reload the same location. And the same goes for rowhammer, because rowhammer is essentially doing flush and reload.
Yeah, I mean, and it doesn't have to be very, very large, right? Like, let's say even if you have a 64 megabyte cache, it is 1 million lines. Millions of lines is actually not that much. It'll take roughly about 4 milliseconds to fill 1 million lines in the cache. You can do it 16 times, right? And if you're activating the row buffer 128 times because of strided access patterns, you reach 1,000 very, very easily. Right. So I do think that like I agree that it's a problem that's just worsening. And there's certain dimensions that are coming from the workload that I don't think we are thinking about, right? It's not just a linear, like 4,000 to 2,000 something works. So it'll work at 1,000, it'll work at 500, it'll work at 250. It doesn't behave that way, right? At some point, your normal applications are that way. And I don't know what happens with the DRAM industry at that point, right? Like,
let me make a point there, actually. Very quick point. If it weren't for TRR, which is today present in many DDR4 DIMMs, we would have bit flips today. That's a fact. So some of the reasons why we don't see bit flips, even with, so this is orthogonal to, so this is on the servers, and this is orthogonal to ECC catching them and fixing them, or detecting them and raising the flag, blah, blah, blah. But we would see bits being flipped, maybe corrected by ECC, maybe not. But the reason why we don't is because, so TRR today doesn't just stop rowhammer, it stops normal workloads on server machines.
Yeah. Irina asked the question whether it's, I think paraphrasing the question is whether it's realistic that applications could create patterns that, that are hammering. Here's an example of one building on something that Moidin pointed out about caches. So on the DRAM chip, each row is typically 64 or 128 cache lines long. So suppose you have two sets of data, vectors that you're processing, say you're adding them together. So you take one from vector A and one from vector B, and you create a result. And those happen to scan two rows, which sandwich a target row in between. If they alternate in the correct way, each time A switches to B, the DRAM chip loses context. It has to switch away from that row, open the other row, and then it has to switch away and open the first row and second row and first row and second row, all the way down that strip, in what from the application's point of view is a totally sane, good pattern of access, sequential access. Now, in practice, the CPUs will have tricks to predict this and maybe mitigate it, but that's just an example of how easy it is to create patterns which amplify the need for the DRAM to switch back and forth. And each time it activates a row, it is causing disturbance on that sandwich row in the middle. These are the kind of unintended effects that can, at 10,000 activations, it's not a problem. But when we get down to 1,000, it's going to matter. We're going to hit it every now and then. It's going to be terribly hard to debug because it will be sporadic. It'll just be a hard to pin down unreliability in the hardware, unless somebody realizes in advance what was going on. I mean, I've seen things like this in the past, like not to go down a rabbit hole too far, but we had a problem with interrupts at one point, which turned out to be that the memory controllers recognized a sequential access from one process, gave preference to it, and locked out the interrupt from the memory long enough to cause the interrupt to fail on latency. You know, there's some very weird effects when you get down into these things, and having a component in there that's fragile, where if you mistreat it 1,000 times in the wrong way, you get an unexpected problem, that's bad news.
Tanj, actually, the patterns that can cause are even simpler, right? Let's say if you're 32 megabyte cache, I have a 64 megabyte data set. I just do random access pattern in a 64 megabyte data set. It's common for linked list to have that kind of pattern. You will go through the entire data set about 16 times, right? You don't get any row buffer locality. And at that point, you will exceed several hundred, right? And these are very, very typical normal workloads. Like linked list is a very common workload, right? So we are getting into an interesting regime, right? That's one of the reasons why I wanted to bring this in, that we typically think about attacker and defender. The next wave is really where, if really the thresholds keep reducing, your normal applications are going to be like that, right? And then whatever we develop really needs to be low overhead and scalable. Otherwise, it just wouldn't work.
So I have a question for the panelists, right? So, and my question is really, how do we break the cycle, right? Because the DRAM vendors are not just going to sit back and do nothing, right? So they also realize that this is a problem, and they're going to come up with a solution, right? And they're going to implement it. They're not going to tell us how they're going to do it, right? So, you know, we're all sitting here talking about, you know, this is going to be bad, and it will be bad, and they will do something about it, right? But then again, 5 years from now, we're going to be in the same situation. So what can we do to make sure that we break this cycle? And I would like to know what you think about that.
I think the most productive thing we can do is to help figure out solutions which are feasible and cost effective. If the industry doesn't come up with them, give them ideas that they can run with. I don't quite agree that they're not going to tell us. I think there's two classes of solution. One is the class of solution that requires JEDEC. That is to say, there's an interface pin or there's an extra command that has to be agreed that's going to be used. And they're going to have to standardize that. So they're going to have to describe it and say what's going on. The other kind of solution is the one where somebody miraculously figures out a way for their DRAM chip to be perfect, and God help them if they tell anybody else how to do it, because that's their competitive advantage. I think there are solutions in that class. Stefan and I suggested one. The industry didn't seem to be terribly receptive to it at the time because it puts some overhead on DRAM and they don't like that. But that might happen as well. How good that is, as you say, if they don't tell you, you don't know. Just put it in a tester and try to break it and figure out what they did.
Yeah, but one would say that then it would be too late, right? Like we are now with DDR4. I mean, we did a lot of reverse engineering, right? And there are a lot of these internal mitigations where they're implementing. Each vendor is doing something else. Actually, they're doing different things for different part numbers, right? And they don't tell us exactly how this works. And then we reverse engineer it, right? And then we understand, okay, we can come up with these patterns that would bypass these mitigations. And then suddenly for the next 5 years, you know, all the devices are going to have bit flips, right? So how do we stop this from happening 5 years from now again, right? So because as Victor said in his keynote, right, by the time you come up with an idea to implement a mitigation, till to the point that it actually makes it to the product, it's going to take 5 years. And if there is not going to be an oversight to make sure that, these things are good, principled, you have certain guarantees. If these things are not going to be in place, then, I have to, look at what has happened in the past and say, if nothing changes, the same thing will happen again.
So Kavik, like, I also want to bring in, like, so people keep bashing TRR, right? But see, TRR was very useful when the threshold was high, right? Fundamentally, it's a moving target. As the thresholds reduce, you need more and more storage to track. You don't want to give that much storage. You cut corners. And then, of course, if you don't track all of the attacking rows, somebody will bypass, right? So fundamentally, the problem becomes, how do you track efficiently? How do you develop better mitigation, right? At least, I think that if you have good trackers that can track efficiently till a couple of hundred, I think we can get there, right? Below that, I don't know what happens.
But this is again very, very focused on Rowhammer, right? And you said you don't want to be focused on Rowhammer.
Okay, so the generalized solution to me is really ECC. In fact, there's a helping hand that's coming, right? DDR5 increases the ECC budget from 12.5% to 25%. You can do a lot of creative things. You can have your Mac, you can have large number of single bit error correction. You can have larger granularity failure correction. That landscape is still like unexplored according to me, right? We've never had that much budget before. And now we have greater problems, right? And ECC is a big hammer that can solve a lot of problems. It doesn't care about why the problem happened, right?
Unfortunately, the reason you get that budget is because the problem is already larger. You've got fewer chips, so when a chip fails, you lose more bits, and that's what's causing it. So most of that increase you just got eaten up by the reason it happened.
So I'm not even talking about chip kill at this point, right? Yes, when a chip fails, you lose 25%. At that point, one chip is not enough, right? Designing chip kill systems with DDR5 is itself, like, I think, a good area of research. But if you don't care about chip kill, right? And systems don't always have chip kill, right? Or is there a way to make take chip kill budget, which is 2 extra chips, figure out a way such that you can tolerate chip kills, you can tolerate few more single bit errors, and you can have a Mac, right? So this is something that we explored for DDR4, but for DDR5, the budget has increased, right? So that to me is a useful area. And this is something that, again, there might be a push-pull from industry. Samsungs of the world or Microns of the world would not want to let you do this at the memory controller because it makes their chip look bad, right? But the Intel and AMD of the world, if they can get extra bits, they can actually figure out a lot of creative things. So I think that might be a way where you relegate some of the responsibility to the memory controllers. I don't think that just hiding everything from the outside world is going to work.
I want to let Irina ask her question also. Thank you for joining us, Irina.
Thank you. So I have one question. What we usually see is mostly DRAM manufacturers are not very open to collaboration between the DRAM and the memory controller, right? So even if they increase, or if we have increased budget for ECC, there would be more effective solutions if there is collaboration between DRAM and memory controller, if those ECC bits are utilized in a better way. That would allow the ECC bits to be utilized in a better way. So I would like to ask the panel, what do they think about having this collaboration more, making this collaboration more possible in future, and that if that they think is a possible solution that can help with whether increased reliability or even increased security.
Reform JDEC.
Yeah, I did actually early on in the quest for what became bounded errors, try to get JDEC to consider making the ECC bits that they use internally available externally. And I think exactly as Irina said, the industry just doesn't want to let anybody see their dirty laundry. And they felt that if they exported these bits, then they would be unable to hide their intermittent errors and you know, it's hard to say because nobody would come out and say exactly why they opposed it, but none of the 3 vendors I talked to at the time were supportive of the idea. They all pushed back and said, you know, we want these bits internally and that's that. I can kind of sympathize with them in that in the consumer side of their business, which is half or more of all of their sales. Nobody's making a controller, an SoC chip that does ECC. So they really had that incentive to make sure they did it inside the chip to get it done. And it did improve the reliability. Arguably, you're somewhat like 10 times better than they would be without it, maybe twice as good as the previous generation. So how do you move an oligopoly that's making $100 billion in profit or revenue a year and 30 or 40 billion in profit? They're very happy with things as they are. Ultimately, we move it by doing the sort of things some of the people here have done, research, showing the problem, rubbing their nose in it, making them
showing that we can do better, showing that we can be not just more reliable and secure, but also more efficient at the same time, because we can then exploit those margins again, those security and reliability margins that we just produced, right?
And they do listen, but very slowly. It took 3 years to get them to do bounded fault. But they did it eventually. You just had to keep talking to them and describing it and having them think about it. And eventually they realized, yeah, it solved one of their problems, which it was a problem they really didn't want to have. So they did it. And now it's happening for all different classes of DRAM eventually. So yeah, we've put forward some of these ideas, better counters, other methods. Don't get too disheartened if they don't say yes immediately. Keep going at it. Keep refining your idea. Listen to why they say it isn't a good idea, why they don't like it. They don't want to think about it. You think about it. Hopefully, some of you are researchers. You get paid for it. I'm a consultant. I have to find somebody to pay me.
Actually, that is well spoken in the sense. Last year, if you remember, we had TK from Samsung who gave this wonderful presentation, and he, you know, one of the things he said upfront was that, yeah, there, you know, Rowhammer is not a solved problem. So that is, you know, the fact that you have one of the 3 companies, you know, participating in the DRAMSec. Now, JEDEC has white papers that have talk about Rowhammer reliability. And in there, you again see how in those specs, how it's clear that Rowhammer is not a complete, they have clear sentences that say that it's not a solved problem. This has happened in just a span of like 1 or 2 years. And it might sound like a long time, but it's incredible on the other hand, how fast it's moving. So I think to sort of echo Tanj's point is that I think keeping at it is an avenue of success.
So this is something that I also want to ask industry folks, right? At some point, there are liability issues. You can't just give crappy products that doesn't even work for regular applications, right? At some point, they could say, well, you know, regular applications don't do this, and we have taken care of it. At some point, this really, really becomes a liability issue, right? Somebody will sue somebody, and like you can't really give products that just don't work, right? So this does become a viability issues for memories at some point, no?
It amazes me that no class actions have occurred yet. I mean, it's like $100 billion industry has got a big target on its back. And if you look around, they're pretty much the only industry that is critical to so many products in our life where there are no standards for reliability, there are no requirements for disclosure, there's no information about long-term reliability, everything's secretive. You know, cars have crash tests. DRAMs have nothing. And yet those cars contain DRAMs. Is your DRAM going to last 10 years? Good question.
So interesting discussions. So I think maybe Stefan, it's time to slowly perhaps close the workshop. What do you think?
Okay, well, if there are any sort of parting thoughts that people have, Victor kind of took a step down and he went into the background. He's just like, You know, so it's just.
I figured I talked enough already. The hour before. Yeah, I've been thinking about the question that Kaveh asked earlier, right? So what can we do to make sure it doesn't happen again in 5 years? My answer would be to stop publishing your papers and just join the JDEC Data Integrity Group and then publish your work there. If you really want to make the world a better place, right? You don't have to go to the media; you just have to go to JDEC.
So just join the smoke-filled back rooms, right?
Yes, yes, because that's where the decisions are being made, right? I mean, it's fine. You can make a nice.
I don't know. I think those back rooms weren't making good decisions before this stuff was published.
No, but
it's antithesis to academia, right? Like we want freedom, like we want to actually talk about our ideas.
Yes, I know, but you also
don't want to go.
But now you're complaining that we are not fixing the problem, right? But you don't. So you're trying to make industry moving into this whole different direction, but that's not how we work, right? We do go to this back door, and that's where the decisions are made, and we do have all these constraints, right? So if you really want to help in making things better, you should just also go and work with the same constraints that we're working with, and go to these backdoor discussions, and then
that is persuasive, except for the secrecy requirement.
Yes,
I mean,
yes.
that there's no real justification for why the industry has to, you know, say anything you bring into JDEC you can't discuss elsewhere, which is
yes. I agree.
I've been criticized for that, for relatively mild disclosures that I thought were perfectly harmless, and the committee got to me and said, no, you can't do that.
Yeah, so that's why I said I was also thinking about the reply, because I also see merit in having academia as like reporting to the public, right? And if nobody is writing about Roham, then no other group will also do the Roham research, and then we won't see this new next level attacks, and then the industry is in this behind doors, and then thinking, okay, everything is solved. I mean, we don't have to do anything. So it's not a solution if you all join JDEC and data integrity, but maybe if 50% of you could join, that would be great, right? Or you could live with like the 20% that we currently have, and then we will talk again in 5 years and then see what will happen then.
Okay, on that note, thank you everyone for participating.